Okay, welcome. Thanks for coming. This is the week 7 webinar for the class. We're actually now in the second half of the class as of, officially now, because we're in week 7 out of a 12-week class. So we just started the second half. The plan today is we'll start out, as always, I'll answer any questions you might have. And then we're going to get into hypothesis testing. Hypothesis testing, pretty much that's what we're going to be doing pretty much for the entire rest of the class. We're going to be looking at hypothesis tests. So today's a biggie. You don't want to, ignore any questions you have or whatever, because you need to understand everything we're doing today, or you won't understand what's going on in the future. So pretty much for every week, weeks 8, 9, 10, 11, we'll be doing hypothesis testing. Okay, there's one little thing called regression analysis that we'll also do in a couple weeks, but pretty much hypothesis testing is what it's all about. So what we're doing today is I'm going to go through the simplest type of hypothesis testing and talk about a step-by-step process for hypothesis testing. So the first step of any hypothesis test is to determine what the null and alternative hypotheses are. That's kind of like deciding what the other guy is saying versus what I'm saying. And that's kind of the null and alternative hypotheses. Then we'll talk about type 1 and type 2 errors. And that's kind of like, well, there's a chance that I'll end up saying that I was right, but I was wrong. Or there's a chance that I won't be able to say I was right and I was right. So either way, it's an error, and those are different errors. So we'll look at those errors. Then we'll look at the level of significance. That's real similar to the level of confidence, except the level of confidence is kind of a probability of being right. Level of significance is really a probability of being wrong. And I actually have no idea why, for some reason, confidence intervals and hypothesis testing switch in terms of right versus wrong. I don't know, but that's how it is. Then we'll talk about the p-value. The p-value is a probability of, if you did the study again and the other guy was right, what's the probability you get what you got, or more, okay, or closer to what you wanted. Okay, we'll talk about how do you state the conclusion, how do you interpret the p-value, how to interpret the level of significance, let you know, just like confidence intervals, but even more, there's gonna be a lot of writing. So you definitely need to know how to, write out all this stuff. And I'll have some templates that will help you out to get going. And then project 1 is over. So it's time to think about project 2. And I'm not going to be getting into all the details of project 2, because that's really next week. Because project 2 is actually all about chapter 10, and we're going into chapter 9. But at least we can talk about planning on it, timelines, things like that. And I can give you ideas of what the project is, but the details you have to wait a week for that one. Okay, so that is the plan for today. I want to ask you, are there any questions about anything? I know it's a small group today, but I'll be happy to answer questions if you have them. No questions? There's no questions. I'll go into the material. Okay, and then if there's anything you don't understand when we're going through this, make sure that you ask. So we're going to be looking at hypothesis testing. So I want to give you, in my opinion, the last 20 years or so, the most important hypothesis test that has happened. And that is when they looked at the vaccination. I don't know if you thought about it, but they built this new chemical and they hoped it would work, right? They couldn't even test it on mice because mice didn't get COVID. Is that true? So the only thing you can do is test on people. And the question is, how do you know if it's time, or when is it time, to basically set it up so that everyone in the world can get vaccinated? How do you know it's safe? How do you know it works? Does that make sense? I don't know if you ever thought about that, but that's really important. And my guess is you didn't, but when the vaccination came out, what I did is I read the test and the studies they did to make sure that it worked before I got vaccinated. And guess what? It did. But I wanted to make sure that they did their statistical analysis correctly before I'm going to, let them give me some chemical. And they did, and I'll talk about it. And we'll see that this actually works. Okay, so when you think about it, what they did is they did a control study. Do you remember what that is? It was the first week of class we talked about a control study. Yeah, I don't see anyone saying they remember. Okay. Yeah, you have a control as a group and that doesn't receive treatment and a group that does. Okay, and I'm going to simplify things. The control study actually works better for next week in terms of talking about it, but because it's an important hypothesis test, I figured we should talk about it now. And that is, you can think about, well, what percentage of the people are getting COVID now? So the question is, if we now get volunteers to get the COVID test, get the COVID vaccine, and then let them play around for a couple months and see if they get COVID. That's what they did. And what they wanted to do is they wanted to say, well, after getting your vaccination, are you less likely to get COVID? Is that clear on kind of how that works? And if you're not less likely, don't give people the vaccine. If you are less likely, then absolutely you should get the vaccine, as long as it doesn't kill you and stuff like that. So they tested that too. Okay. So what they did is they ran a hypothesis test. So again, they gave a bunch of people the vaccine, but what they did is a hypothesis test is the following. Okay, at the time, about 4% of the population was getting COVID. Okay, over, I don't remember the month period, but it was like a couple months. In a couple months period, about 4% of the population was getting COVID. So what we're going to do is we're going to write, and this is important, these symbols are always going to happen for every hypothesis test for the rest of this class. And again, almost everything we do for the rest of this class is hypothesis testing. So the first thing we have is H. Okay, hopefully you all know. What do you guess what H might stand for? Yeah, that's hypothesis. Okay, the good thing about math people is we're boring. We don't like do tricks and stuff like that. Okay, then we have a subscript. And I call it 0, but that's not what the statistics world calls it anymore. And that's because the British got to it before the Americans. Anyone know how to say 0 in Britain? Z. Z is one way, but not N-A-U-G-H-T. So the way I'll say it, and you'll hear me say this a lot, is H not. It's not N-O-T. It's N-A-U-G-H-T, and N-A-U-G-H-T that means 0. Okay, and that's the British way of doing it, and that's who kind of came up with the stuff. And then note right here is a colon. That's not an equal sign. That's a colon. Okay, 2 dots. Any questions so far? Okay. By the way, I don't care if you're doing your exam or a discussion board and you don't know how to make that sub-0 happen and you just put 0, that's okay. I'll let that happen. On your project, you should make it work because that you can get help with. Okay. And then in terms of COVID, either you test positive or you don't test positive. Isn't that true? You don't test half. I don't know if any of you gotten COVID, but it sucks when I got it and I tested positive, but then fortunately, all the other tests I'd ever done, I tested negative. Okay. It's a yes, no survey question. Any questions on that so far? And with a yes, no survey question, we're talking proportions. And P, do you remember, stands for the population proportion. Any questions on that? Okay. So just note, in our class, we will always use an equal sign for the null hypothesis. We're looking at the null hypothesis right now, or an H naught. So P is equal to 0.04. And the idea is the other guy is saying, well, this vaccine does nothing for you. You're still going to have a 4% chance of getting COVID. Do you see that? Okay, it's a debate. Hypothesis testing is a debate. The other guy says, no, it's what it always has been. This vaccine does nothing. And they say the population proportion is 4% when you get the vaccine because it hasn't changed. Any questions on that idea? Okay, then there's the alternative hypothesis. Okay, always still H for hypothesis. And our book and most books actually, but not all of them, use a sub 1 because after 0 is 1. Occasionally you'll see an A for alternative. You'll see either of those. Just want to give you a heads up in case. And that means the alternative hypothesis. And then still a colon. And then we still have the population proportion. But now what we're trying to show, right, if we say are working for Pfizer or something, is we're trying to show the proportion of people who get COVID after they get vaccinated is less than the 4%. Because we think that we want this vaccination to be approved by the FDA. And if it's less than 4%, in other words, if it drops your chance of getting COVID, the FDA will say, great, use it. Okay. Okay. And of course, there's more details. You have to make sure it doesn't kill you and all that stuff. But I'm just doing this piece of it. So we're going to have P less than 0.04. So I want to stop. Are there any questions? Any questions about this example, which is, like I said, a real example? Okay. They had a sample size of around 20,000. Okay. And you need a pretty big sample size when you have a small proportion like 0.04. Otherwise, you don't really get a good study. Okay, so H sub 0 is a control. Yeah, H sub 0 is kind of like the control. Okay, so H sub 0 is what you're trying to show is not true. H1 is what you're trying to show is true. So the control in this case is what you're trying to show is not true. You're trying to show that people are not getting that. Okay. The word control is not quite right, but I'm not going to get into that. Next week, we'll talk about it. But the idea is right, and that's what matters. Okay, so the next thing is to state the ramifications of a type 1 and type 2 error. I just want to let you know, in case you don't know this word ramifications, this is not a statistics word. It's an English word, but not everyone knows what it means. It's the bad stuff that happens because of it. Okay? What goes wrong, who gets hurt, that kind of thing. That's what ramification means. And then there's going to be what's called a type 1 error. There's going to be a type 2 error. Okay. And kind of in medicine, any of you in medicine by any chance or want to be in medicine? Like nursing or something like that? If not, you've probably heard of this anyway. Often you'll hear of a false positive and a false negative. Have you heard those words before? Yeah, it's especially used for medicine, but it really works for just general hypothesis testing. So the type 1 error is a false positive. So the idea of a type 1 error is you're saying that you're right, P really is less than 0.04 based on your sample, but actually your sample didn't do, was not typical and you weren't right, okay? That's a false positive, okay? And also called for our class, it's called a type 1 error. A type 2 error is the false negative, and that means that we do not have evidence to show that the vaccination is working, or in this case, the P is less than 0.04, when it really is less than 0.04. So that's what type 1 and type 2 errors are. And let's look at the ramifications. Okay, for the type 1 error, the idea is we're able to show, or we're saying, we're able to conclude that the proportion is less than 0.04 when it wasn't. Okay, and that's bad, by the way. Okay, so the ramifications, well, if your testing ends up showing this vaccination is actually reducing COVID, when it's not, what's going to happen is the FDA is going to approve the vaccination, right? But unfortunately, it doesn't work. So people are going to have to go through getting vaccinated, and it does nothing for you. Okay, I don't know if you all got vaccinated, but for me, I mean, I didn't die or anything, but the next day I was so tired. I wouldn't do it by choice if it didn't help. And my guess is you wouldn't get vaccinated if you knew it, if it didn't help either, right? So the vaccination gets approved, lots of people get vaccinated, but it doesn't work. So you have to go through that vaccination process. You're going to be so tired the next day. You might even be overconfident, right? Because after I got vaccinated, I went and saw family because then I wasn't as worried. Okay. And maybe you might get COVID because you were like overconfident that you wouldn't get vaccinated, that you wouldn't get COVID. Do you see that? So notice that's bad. Type 1 error and type 2 error are always bad. Any questions on that? Okay, type 2 error is the opposite. That means you're not able to show that P is less than 0.04. So if you're not able to show that P is less than 0.04, then the FDA is not going to approve the vaccination. Okay? But the vaccination works because it's an error. So we don't have enough evidence to reject the null hypothesis. We also call that we failed to reject the null hypothesis when the null hypothesis really was false and the alternative hypothesis was true. So in this case, the ramifications is that we have this vaccination that works, but nobody gets vaccinated because it didn't get approved. That's bad, right? So maybe 1 million more people still die of COVID because nobody has a vaccination to get. So COVID just keeps being rampant and kills more and more people. Okay, that's a pretty bad ramification too, isn't it? Notice they're very different. Any questions so far on these ramifications of the type 1 and type 2 error? Okay, so the next thing we have to do, and you have to do this also with confidence interval. With confidence interval, you have to decide what the confidence level is. Are you going to use 95%? You can use 99%. You can use 90%. Similarly, we're going to have to decide, and this is after looking at the type 1 and type 2 error. What should the level of significance be? Okay. And the level of significance is kind of the probability of a type 1 error. So it's the probability of you saying that P is less than 0.04 when actually it isn't. Okay. If a type 1 error is really bad compared to a type 2 error, then we want a much lower level of significance. In other words, you want like a 0.01, 1% instead of 5%. So you want a much smaller chance of being wrong. If the type 2 error is worse than the type 1 error, then you're going to use a level of significance of like 10%, because then it's not as bad to be wrong for the type 1 error, and type 2 is bad. Any questions on that idea? Okay, so in this case, you have to decide, and this isn't math actually, this part. You have to decide what's worse. Okay. In our class, again, we're going to stick with 0.01, 0.05, or 0.1. So 1%, 5%, or 10%. Those are the choices. The standard is 5%. And for our class, if you think the type 1 error is worse, then you're going to use 1% or 0.01. If you think the type 2 error is worse, you're going to use 10% or 0.1. If you think they're kind of similar in how bad they are, then use 5%. Okay. And what matters is you need to be able to explain why it is that you think it's true. Okay. There isn't necessarily a right answer, but there's a right explanation. Any question on that? Okay. So the next step, actually, I didn't write this down, but the next step, actually I did. So the very next step is the hardest step of the entire thing in the real world, but we're only going to do it once in this class. So the next step is to collect the data. And you might have to, with that vaccination thing, we're talking about getting 20,000 volunteers. Actually, they got 40,000 because 20,000 got the real stuff. And then you're going to have to, find medical staff to give them the vaccination. You're going to have them come back, and you're going to have to test them to see if they're positive or negative. That's a lot of work. Okay. This class, we don't do that work all the time. I'm just going to tell you what happened, and then you're going to have to analyze. But I want to give you, a heads up on reality. In reality, that's a lot of work to collect the data. Okay. Again, you had to collect data where your sample size was like over 30, like 31 or 32 or something. But if it's this vaccination thing, we're talking tens of thousands. That's so much harder. So I want to give you that heads up. And then once you've collected the data, then you're going to put the data into the computer. And you're going to calculate what's called the p-value. Okay, you're going to compare the p-value with the level of significance. I'll explain in a little bit what all that means. If p is less than alpha, then you're going to reject the null hypothesis and accept the alternative hypothesis and say, I was right. If p was greater than alpha, you're going to fail to reject the null hypothesis. And you're going to say, you're not going to say I was wrong. It's a weird thing in statistics. You never admit you're wrong. You only say, I don't have enough evidence to say I'm right. It's a weird thing, but that's how it works. So let me show you a picture. So the picture that we did is 0.04. 0.04 was the percentage of people that were getting COVID at the time when they did the vaccination, okay, when they did the first tests, okay? And it turns out that after getting vaccinated, 1% of the population who got vaccinated got COVID. Okay, it doesn't mean no one got it, but it was 1%. Now that's less than 0.04, but is it less than enough? Does that make sense? So since we had a sample size of 20,000, NP and NQ were definitely bigger than 5. So we were able to use, or they were able to use a normal distribution. And when you have a normal distribution, you can draw this beautiful picture with the normal distribution on it. And then the area to the left in this case, because, and I want to show you this, in the the alternative hypothesis, we have a less than sign. We want p to be less than 0.04. So that means we want to be on this left side, because less than 0.04 is way to the left. And the area to the left of the value that you found, in this case, 1% of the people got COVID. Okay, 1% of the vaccinated people got COVID. The area to the left of that is called the p-value. Okay, we're going to be using this p-value over and over and over and over again in our class. Okay. Okay. So what they got for the p-value was 0.004. That area is a very small area, it turns out. Okay. And again, they didn't use my calculator, but something like it. They used a calculator and they got the p-value for this hypothesis test, and they got 0.004. That is very small. Okay. It's smaller than 1%, and that's a level of significance they might have used because a type 2 error is actually worse than a type 1 error in this case. Okay. So they use 0.01, 0.004 is definitely less than 0.1. If the p-value is less than 0.1, we get to reject the null hypothesis, and we get to state the conclusion we were hoping to state. And here it is. There is statistically significant evidence. And by the way, if the p-value is really small, and this one's tiny, like less than 1%, sometimes we'll say strong. If the p-value is like 0.04, it's small, but not as tiny as 0.004. And then you wouldn't use the word strong. Okay, but there's strong statistically significant evidence to conclude that the population proportion of vaccinated people who get COVID is less than 0.04. Okay, I want to mention I have highlighted in red statistically significant evidence. Any guess on why I highlighted that in red? I've done this many times now in this class, and I've asked you. And I also highlighted in red the word population. Yeah, if you don't use that vocabulary, what's going to happen? Yeah, so if you don't use the vocabulary, what will happen? I will take off points. And by the way, I graded your discussion posts about confidence intervals. And if you didn't refer to the population or have the word all Americans, I took off a point. So just let you know that, I'm good to my promise, by the way. No matter how much you don't like it, if you don't have those words, I take off, you lose points. Got it? Because it's really important to be able to specify that that's what you're talking about. And if you're not listening to this video, that doesn't matter anyway, because you'll lose points and because you didn't even know. But you're supposed to listen to every webinar. Okay, whether you watch on YouTube or we watch it here live. Okay, so any questions on this? Is the conclusion, by the way. If they say state the conclusion, that's state the conclusion. Okay, because that's the most important thing. Because at this point, if there's strong statistically significant evidence to conclude the population proportion of vaccinated people who get COVID is less than 0.04, then what does Pfizer get to do? Or if they're able to have this conclusion, what do they get to do? Yeah, they produce a vaccine and even more important, give the vaccine to people, get people vaccinated. Okay, and the FDA approved it and then lots and lots and lots of people got vaccinated. Okay, and again, I look at the statistics. You can trust me. You could also look at the statistics and you'll see it really does work. Okay, does not mean that you have a 0% chance of getting COVID, but it means that it definitely reduces your chance of getting COVID by getting vaccinated. In fact, I think I'm going to get vaccinated for that'll be my fifth or sixth shot in a few weeks because it's that time again. Okay. So then you might be asked to interpret the p-value. So remember, the p-value is this area here, which is the probability of being less than this number, this 0.01 that they got, given this 0.04 is true. So given the null hypothesis is true, it's the probability of getting something is at least as extreme as what you got in the alternative hypothesis. Okay, I'm sorry, as what you got on, not in terms of, as what you got in the study to show the alternative hypothesis. That's what the p-value is. It's that probability. And by the way, if this had been a greater than instead of a less than, then you'd find the p-value by looking at the area to the right. You could also have a not equal to, and then you'd have the p-value, you'd have a two-tailed, and you look at the two tails, add up the areas, and that would be the p-value. Okay, so here's how you interpret the p-value in this case. If the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 people were vaccinated and COVID tested, and at the end of the testing time, okay, at the end of the testing time, then there would be a 0.4%. So by the way, 0.004, if you move this decimal place 2 places, that makes it a percent, and it's 0.4%. There would be a 0.4% probability that fewer than 1%, because that's this 0.01, of them would get COVID. Okay, there's no short way of saying this. If you think there is, you're wrong. Just let you know that. Okay, I'll let you read this for a moment. I'm going to pause just so that you see it, because it's important that you get this down. If you have questions, ask where all these numbers came from in the words. Okay, so if not, then let's look at the level of significance. So we want to interpret the level of significance. Remember, our level of significance was 0.1 or 10%. And the level of significance, by definition, is the probability of a type 1 error. So type 1 error means the null hypothesis was correct, but you accepted the alternative hypothesis. So the null hypothesis was correct, and you accepted the null alternative hypothesis, you can say the following. So if the population proportion of all vaccinated people who get COVID is 0.04, that is a statement of the null hypothesis in words. And if another study of 25,000 were vaccinated and COVID tested during and at the end of the testing time, okay? So in other words, if you got another sample of 25,000 people and did the same thing, then there would be a 10% probability, okay? 10%, that was our level of significance, okay? 0.1 is 10%. So there would be a 10% probability we would end up falsely concluding that fewer than 4% of all vaccinated people get COVID during these months. Okay, that's another way of saying it's the probability of a type 1 error. So I'll let you read that one for a moment. Again, I strongly recommend writing this down, getting kind of a template, and having the idea down so you can handle this. Always note, by the way, if it's about a mean, don't use the word proportion. If it's about a proportion, don't use the word mean. I noticed that with the confidence interval, some of you made that mistake, and I take off points for that. Okay, it is important that you have your statistical vocabulary correct. Okay, any questions? Okay, note, by the way, at this point, we're not worried about a type 2 error anymore, because the type 2 error means that you failed to reject the null hypothesis when the alternative hypothesis was true. And we didn't fail to reject, so we don't have to worry about that. The worry would be the type 1 error, which is a worry, but not a huge worry because it's a very small percent here, right? The p-value is very, very, very small. There's a concern, but it's a very small concern of a type 1 error. Any questions so far? Okay, so let me give you another example. And I know most of you probably aren't even from Lake Tahoe, but I'll tell you, one of the biggest things that we care about in Lake Tahoe is that we keep our lake blue, is what they say. Keep Tahoe blue. So we want to make sure that we don't have mess coming into the lake. Okay, and there's lots of different messes. And I will let you know, there's a community effort every year that happens at the end of May here, if you ever up here. And that is the whole bunch of volunteers go and they take samples of all the water that goes into Lake Tahoe, and we measure it and we give it to a bunch of scientists, and then they do statistics, and I've actually helped them with statistics to see whether or not there's endangerment to Lake Tahoe. So one of the measurements that are done, and I've done this every year, I do this volunteer thing, is I go to our nearby creeks and I measure the pH, okay, in these streams that flow into Lake Tahoe, okay? And so do a lot of other volunteers. So one big question is does the average pH in streams that flow into Lake Tahoe differ from 7.0? I don't know if you don't know any chemistry, that's okay. But the pH of pure water is 7.0. And we'd like it to be water, right? Don't want it, if it's lower than 7, you call it acidic. You've heard of acid. If it's higher, you call it basic. That's base. You don't have to know any chemistry for this class, but I figure I might as well mention it because that's what we're talking about. Okay. So, and by the way, if it's acidic or basic, that's bad. So in this case, we probably want to do a two-tailed test. So first, H naught. Again, this is going to be, let me see this view. There we go. Okay. This is, when you look at the pH, it's a number like 7.3 or 5.9. Okay, it's not a yes/no question. Okay, you measure the pH and you get a number. Okay, so because of that, we're not going to use P, we're going to use mu, because we're looking at a population mean, we're not looking at a proportion. So we're going to get mu, and there's the mu, and then we're going to have equals 7.0. And H1 also is going to be mu. And now, again, if it's on the low side or the high side, it's bad. So in this case, what we're going to do is what's called a two-tailed test. And for a two-tailed test, we use a not equal to 7.0. Because if it's not equal to 7.0, that means that it's not pure water. Any questions on that? Okay, so now we look at the type 1 and type 2 error. So a type 1 error means that we have statistically significant evidence to show the pH differs from 7 when it really is 7. So we actually have statistics to say, hey, we got a problem. The water coming into Lake Tahoe is going to mess Tahoe up. So what's going to happen is the government's going to fund a very expensive project to mitigate the pH issue in the creeks. But it turns out we were wrong. The pH really was 7, and there was no problem, and it was just a total waste of money. That's a bad thing, right? You don't want to waste money if you don't have to. Any questions on what the type 1 error in this case is? Okay, type 2 error is, that's the kind of the false negative. It means that we did not have evidence. Okay, we didn't have evidence to support the claim that pH differs from 7 when it really did. Well, if we can't show that pH differs from 7, the government's not going to give money to change the pH and to improve that. So no funding is going to get put into the mitigation. But unfortunately, the pH really wasn't 7, and the Lake Tahoe plant and animals are going to go extinct. We're going to destroy our lake. It's going to be terrible. So which do you think is worse, a type 1 or a type 2 error in this case? And this depends on your, I don't know, maybe political side. Okay. Yeah, I think type 2. I think type 2. But you might think type 1. If type 2 is worse, we're going to use 0.1. If type 1 was worse, you use 0.01. If they're equal, you use 0.05. So you use 0.1. Okay. So now I'm going to tell you, let's suppose that X bar was 6.4. Okay, X bar, remember, was a sample mean. So sample mean pH was 6.4. And S, the sample standard deviation, was 3.5. Okay, this all comes from the data that would be collected. And then N was 15. Okay, and that's because you can only get so many volunteers to do this testing. Just let you know, they do their best. I'm not in charge, I just volunteer. But if N is less than 31, then we must assume the distribution of pH levels is normal, which may not be true. Okay, so that's a big, weird assumption. Okay, but with this example, that's what you'd have to do. Any questions on that? I want to let you know, again, I graded your discussion, I graded your exam, and you need to back up your reasoning for stuff. And a lot of you didn't back up with the sample size when you talked about the normality assumption. So if you need to talk about the normality assumption, you need to back it up with your sample size. That's a requirement. And I told you that last week and the week before, but not everyone listens. So I'm telling you again, maybe you'll listen this time. Okay. Okay, so now that we have that, we can go to the calculator. Which calculator do you think I'm going to use? Which one do you think is the right one? Okay, you say 15. The problem with 15 is that is with data, and I didn't give you data. I gave you statistics. So yeah, so someone else said mean with statistics, hypothesis test for a mean with statistics, and that's the one we've got. So I can click that one. And in this case, sigma is unknown. And by the way, sigma in the real world is always unknown. No one knows the population standard deviation. Just let you know that. Okay, sigma is unknown. So our S is 3.5. Our X bar was 6.4. So 6.4. Our N was 15. And our mu naught, so you find the mu naught by looking at the hypothesis. See H naught? Mu naught is a number that mu is equal to an H naught. In this case, it's 7. And then if you look at this, we have a not equal to sign, right? We're two-tailed test. So we need to click on the not equal to. Okay, it's very important that you pay attention to everything you have to click on. And then hit calculate. Okay, notice that we have T for the test statistic. Remember I mentioned if you don't know the population standard deviation, we're talking about for a mean, then we have to do that little adjustment from the normal distribution. You use what's called the student's T distribution, and that's what happened here. So T is negative 0.66394. The p-value is 0.52, I'll call it. Round to 2 decimals. Okay, so the test statistic was again negative 0.66. The p-value is 0.52. And now, if you look at the picture now, it's a two-tailed test. Remember, 6.4 is what they found. That was the pH of that was the average pH for the sample. 7 was the null hypothesis. That's pH of pure water. If you want a two-tailed test, and notice 6.4 is 0.6 to the left of 7. If you go 0.6 to the right of 7, you get 7.6. Any questions on how I did that math there? So if you do 7 minus 6.4, you get 0.6. If you do 7 plus 0.6, you get 7.6. And that is the right-hand side of the two-tailed test. So we get this area here plus this area here, the left plus the right areas, will give you 0.52. Okay. So the conclusion. So what do you think? Do we have statistically significant evidence or not? What do you think? Do we have statistically significant evidence?
Yes.
Okay. I'm not sure if you're trying to say something, but I can't really hear you. Let me put my volume up. Maybe that's the reason. Okay. Well, our p-value here is 0.52. If there's a 52% chance of like blowing it, that's not good. Then you're not going to say, yeah, I'm right. Do you see that? It's just not that unlikely. It's just not that unlikely to get something as extreme is 6.4 for the pH. So you're not going to say that, no, it must be not 7, because we're not that far from 7. Do you see how that works? So the answer is there is, so let me write down, since P is equal to 0.52, which is certainly greater than 0.1, because that was our level of significance, there is statistically insignificant evidence to support the claim that the population mean pH of water that flows into Tahoe differs from 7.0. Notice having statistically significant evidence does not mean it differs from 7.0. It doesn't mean it is 7.0. It means we just don't know. There's a good chance that our sample size is too small. Our sample size was 15. So when your sample is small, you usually get statistically insignificant evidence. Let me do this. Statistically insignificant evidence. I'm going to highlight in red because those are important words you got to have. And the word population, got to have those two. Got to have that one too. And don't use proportion if you mean mean, and vice versa. Okay, to save a little time, I'm going to not type out what it means to have the p-value of 0.52. What I'm going to do is I'm just going to say it. So what we can say is that if the null hypothesis is true, so in other words, if the mean pH of water that runs into Tahoe, the population mean pH of water that runs into Tahoe is 7.0, and if we did another study where we measured 15 streams that flowed into Tahoe, then there would be a 52% chance of having the sample mean pH either being less than 6.4 or greater than 7.6. Any questions on the interpretation of the p-value? Okay, let's interpret the level of significance. And remember, the interpretation starts the same. The first sentence or two is exactly the same. So if the population mean pH of water that flows into Tahoe is 7.0, and we did another sample of 15 different creeks that flowed into Tahoe and measured their pH, there would be and this is where things change, a 10% chance that we'd end up falsely concluding that the population mean pH of creeks that flow into Tahoe differs from 7. Any questions on this example? Any questions? Okay. Let's do another one. I'm going to do this one a little bit shorter. Let's suppose you want to see if women are not drinking the recommended 2.7 liters a day on average. That's how much you're supposed to be drinking, by the way. By the way, this is like good water, that kind of stuff, not alcohol. But you're supposed to get enough water. Okay. Are you drinking enough? Okay. And let's suppose we decided on a 0.01 level of significance. Let's suppose that we surveyed a bunch of people. First person was getting 2.4 liters, second was 2.8, third was 2.9, next was 2.2, etc. Okay, how do we find the p-value? First thing, what's H naught, H1? So what's H naught? Well, that's going to be mu is equal to 2.7. And H1. And not drinking the recommended 2.7, that really means they're drinking not enough. Okay, so that's going to be mu is less than 2.7. All right, so let's go back. What calculator should I use? Which calculator is the right calculator to use? Because that's really important in this class to know what calculator to use. Yeah, it's going to be 15 because we're doing a hypothesis test for a mean, and we have data. So I click that. And I put in my data. Good thing I was able to copy and paste it in. We don't know the standard deviation, so leave that blank. Less than is what we wanted for H naught. Mu naught was 2.7. And we calculate. And we get a test statistic of negative 1.9 and a p-value of 0.03. That was negative 1.9 again. So the conclusion is there is statistically, okay, is it significant or insignificant? Which one? Evidence. Significant or insignificant? Here's a hint. This is greater than 0.01. That was our level of significance. So if the p-value is greater than the level of significance, it's statistically insignificant. Is that clear? Evidence to conclude that the population mean amount of, let's call it fluid, that women drink is less than 2.7 liters per day. Any questions at all on this? Okay, just note I wrote some templates out. So a template is there is statistically, it's either going to be insignificant or significant evidence to support the claim that the population will either be mean or proportion, and then whatever you're talking about. So I call that a template. Okay, and the p-value template is if, and then whatever the null hypothesis is true, but you should write down what that says in words. And another sample of however many you took was taken. Then there would be and that would be the p-value probability that, and then the results of the new study would be at least as extreme as the results of this study, but in words for the study. Okay, and similarly for the level of significance is if the null hypothesis is true, again, that should be whatever it says. And another sample of however many were taken. Then there would be whatever the level of significance probability that the new study would result in falsely concluding that the alternative hypothesis is true in words. So I just have some templates for you to have. And again, I went pretty fast, but you can always go back and rewatch the video and then look at it if you need to. All right, I thought I'd give you one for what's going on today. By the way, what's the big thing going on today? Yep, Halloween. Okay, might be able to see my background. Okay. So let me ask you, what percent of Americans do you think their home is haunted? What's your guess? What percent of Americans think their home is haunted? What do you think? That they think that their home has ghosts and things like that. I think I'll take the middle one. I see 2%, 14%, and 65%. Let's go for 14%. Okay. Oh, maybe I'll go for 2% because I just realized I think I want to do something. We'll go 14. That is the middle. Do more than 14% of Americans think their home is haunted? Run the full hypothesis test. So let's go H naught first. All right. Is this a mu or is this a p? Yeah, this is a p because this is a yes/no question. It's see if you can put yes or no. Do you think your home is haunted where you live? See if you can answer that question in the chat box. Okay, none of you think it's haunted. Notice you said no. You didn't say 34 or something. You gave yes, no. So that's going to be a P. P equals 0.14 because that's what we're testing. H1 is P. What inequality should I use now? Yeah, more than, greater than, because of the word more than. Always look for the keywords. So more than or greater than 0.14. Okay. They actually did a study. Okay. And I read an article, and with their study, their sample size was 1,017 people they surveyed. And their p hat was 0.16. Okay. P hat, by the way, is a sample proportion. Don't forget about that. So now let's go back to the calculator menu. Which calculator should I use? Yeah, this is calculator 16, hypothesis test for a proportion, because it's a yes/no survey question. We have a P in our H naught. Our N was 1,017. Our X, how do we get our X? How do we get the X? Yeah, we take four, actually not quite. It's not 14% of 1,017. That's not the X. That would be our NP actually, to make sure we're bigger than 5, and that is bigger than 5, by the way. It's actually 0.16 times 1,017. Okay. Because 16% of the sample said yes, their home is haunted, or at least they think their home is haunted, out of the 1,017. So then if I go to the scientific calculator, I can take 0.16 times 1017. And you should always round because you can't have 0.72 people saying yes. So I'm going to say 163. Any questions on that for X? The P naught? What was the P naught? So what's a P naught? Yeah, 0.14. Okay, so P naught is 0.14. And our alternative hypothesis has a greater than sign. So we have to click greater than and hit calculate. Okay, now it's Z, by the way, notice that. It's never T with proportions. So the test statistic is Z equals 1.86. And the p-value was equal to 0.03, 0.0312. Okay, notice this is one of those where if you have a type 1 error, or if you have a type 2 error, is it that big a deal? Yeah, probably not. Okay, type 1 error meant that, you said more than 14% think their home's haunted. Not a lot's going to happen. Okay, when it really wasn't. And type 2 error means that it really was, type 2 error means that it really was 14%, but you weren't able to say that. I mean, it really was greater than 14%, but you weren't able to say it. Either way, it's kind of similar. I'd say this is definitely a 5% level significance. So the p-value is less than 0.05. So what's the conclusion? There is. What's the next word? Actually, statistically. And what's the next word? Significant. Evidence to conclude that more than 14% of all Americans think their house is haunted. Any questions at all on this example? Okay, hopefully you see how important this stuff is. Because if you don't have this evidence, then you're just guessing. Do you see? This is a way you're able to say, yeah, I have evidence to show. Doesn't mean you know 100% certain. Okay, but it means that you have, you're probably a good chance that you're right. Does that make sense? Okay, so again, this is used everywhere. We saw that, I explained that it's used in healthcare. Anytime the FDA approves something, they basically always have to have some kind of statistical analysis, and it always involves a hypothesis test. Okay. Anytime you just about anything you do in science, then you go out and you do a sample and make sure that it does what you think it does in science. Anytime you do it in sociology or psychology, you do a sample and make sure that your idea was right. This stuff is used pretty much everywhere. Okay, there's only one major field actually where if you get, say, a master's degree or a PhD, you have to write a thesis, that you probably will not be using statistics and hypothesis testing. And it's kind of funny. Do you know what degree doesn't use a hypothesis test? And pretty much anything in that degree. Now, art can, because you want to find out, for example, do people like this kind of art more than that kind of art? Is this more outstanding? Does this color work better? That kind of stuff. Should I tell you? Math. Yeah, math. Math is really the only degree, because with math, it's a proof. You have to be 100% certain. You don't take a sample and see if most of my examples work, so it must be true mathematically. No, math is really the only one where you actually have to know with 100% positivity that it's true. Pretty much in every other subject, you do a hypothesis test, which means there's a chance of being wrong, but you want that chance to be small. And again, the standard is 5% for your level of significance. And that was set up by the New York Times, actually, in like something like 80 or 90 years ago. It's been around a long time. And that's how this stuff works. So it's really, really important, this hypothesis testing stuff. Okay. And in fact, we're doing a hypothesis test. If you think about it, we did it for a mean, and you did it for a yes/no question. What else might hypothesis testing be used for besides a mean or a yes/no proportion? Any thoughts? What else might you want to do? Yeah, you could do sums. You could do hypothesis tests for sums. It turns out we won't in our class, but it can be done. Okay, there's actually a whole lot of others. One biggie that's going to happen next week is comparisons. Who's bigger or who's smaller? Who do people like more? This group or that group? Do you see that? Where there's two different groups. And we didn't do anything like that in any of these examples. Okay. Another thing that's going to happen is, what other kind of survey questions are there besides yes, no questions and quantitative questions? We've had this, I know it's been a long time, it was chapter 1. Remember? Yeah, categorical, where it's not yes, no. Okay. And that might be, what is your race? And you might want to look at, the race of people who get a job versus don't get a job, for example. And is there a difference in that, kind of racial categorization, that kind of stuff that could happen. So there are a lot of others. There's another one called regression analysis we're going to spend a whole week on. And that's a biggie too. So I want to let you know, hypothesis test is used for a lot of different things. I don't know if I'll do these examples, but I have them just in case. Maybe I'll just run through them really fast. So things like, the majority of people want to eat instead of drive while in a car. Okay. Like when you get to work, you probably don't get to work like I do, but when you get to work and if you're driving to work, do you really want to spend all that time sitting in front of your wheel looking at the road all the time? Or would it be nicer if you didn't have to do that? Do you see that? Right? I think in 30 years, no one will ever have to do that. How come? Yeah, tech, self-driving cars. But the question is, do people want it? Do people want to be driving, or would they rather sit there and have their lunch and look at their phone and all that kind of stuff? Okay. So you can do a hypothesis test. Okay. And there was a test done, and the word majority. So I'm giving you this because it's important that you know these words. Majority means more than 50%. Okay. Does that mean at least 51%? What do you think? Yeah, definitely not. Let me give you one of my favorite example. When I ran for office, in my first election, I got the majority of the votes, but I did not get over 50%. Yeah, I got about 50.01%, just around that. I won by 3 votes, by the way, out of tens of thousands of votes. Okay. And I wasn't even close to 51%. I was closer to 50%, but I was over 50%, so I won. Okay. So just a note, the majority means anything over 50%. Don't write 51%. Do you see that? Okay, so a P would be 0.5, P, and then greater than 0.5. Okay. So that's what you would do. Does that make sense? Okay, let's look at another one of these. Okay, normal body temperature is 98.6. You probably know that, right? In Fahrenheit, by the way. Is the average different for marathon runners? What do you think? So if someone's running a marathon and you test their temperature when they're just finished, do you think they're going to have a different body temperature? Okay, so maybe, maybe not. But the only way to find out is to test people. Does that make sense? Wait till they're done and you take the temperature of each of your group that has finished the marathon and you test them. By the way, you're going to use mu or P for this. Yeah, you're going to use mu. Okay, because this is a quantitative survey question, not a yes/no question. Okay. So again, these kind of examples can be done. Since we've already done some, I don't want to waste your time too much. So I want to kind of show you examples and not just to go through every one because that will take all the rest of the time. Okay, but hopefully you get the idea. So what I want to tell you is the secret word. And remember, the secret word is always an important word of the day that you may not just like randomly guess. And that is statistically. Because remember, you have to have either statistically significant or statistically insignificant when you're writing your conclusion for a hypothesis test. So statistically is an important word for this particular chapter. Okay. I want to let you know that we're not done. We still have more to do. Because what did I tell you? Those who got here on time, what did I tell you that we were going to do at the end? Yeah, we got to talk about project 2. And we're going to talk about some today, and then I'm going to talk about more next week, just let you know, because we don't have the statistics yet to do project 2. You have the statistics to think about it, but not to do. Just let you know that. Okay. But I want to let you know, what's your guess on the 2 most important pieces of project 2 that you're going to have to analyze? And you might be able to guess, given that I'm asking you, at this point, and if you think about since project 1. Hypothesis testing is one. What's the other one? Yeah, your spelling was interesting. Confidence interval. Yeah, confidence interval. Yeah, hypothesis testing and confidence interval are going to be the 2 things that you're going to focus on. Okay, so let me pop in here and let me remind you a few things. First thing is that the rules of the project 2 are the same as the rules of the project 1. Okay, are you allowed to work by yourself? Yeah, definitely not. Don't even think about it. Same thing, there's a 25% penalty if you can't work with another student. So the first thing I recommend doing is either ask your partners that you worked with and ask if they'll still work with you. Or if you want to change partners, then post on the project discussion board saying, hey, I'm looking for partners. See if you can find new people. And that's already been done, by the way. Some people have already done it. Not by everyone, but some people have already posted. So you'll see that, possibly depending on which section you're in. But make sure, and again, it's less work if you have 3 people than if you have 2. Because if you have 3 people, then you have to do 1/3 of the work. If you have 2 people, you have to do 50% of the work. So, and also if you have 2 people, there is a probability that's not that low that your partner will drop out and you're screwed. So if there's 3 people and 1 person drops out, then you're still okay. So that's just a note, is 3 is better than 2 if you can. It's not like I don't give you a better grade with 3, but just disasters happen less often when there's 3. Okay. What happens more often is you don't like one of your partners, but I can't do much about that because there's 2 people not to like, and you have a higher chance of one of them not liked. Okay, so that's just a note. So that hasn't changed at all. The timeline, let me put this up here. Project 2 is due December 10th. Okay, project 2 is due December 10th. That is actually Sunday of week 11. I do want to give you a heads up, and I'll probably remind you again just before. It turns out that Friday, Saturday, Sunday, before your project, when your project is due or before your project is due, I'm actually going to be at a conference, and I'm helping run the conference, and I'm a presenter, a speaker at the conference. So I might look at my email once a day, but I'm not going to have a lot of time that weekend to help you. So I want to give you that heads up. So wait until the last minute. If you're going to get my help, it won't happen. But if you ask, maybe the week before, then I'll definitely help you and I'll have lots of time. Does that make sense? So I want to give you, a somewhat apology that it's my super busy weekend. So you're not going to get much help from me that weekend. So don't wait till the end. If you wait till the end, I won't be able to do much for you. And I apologize, but hopefully you understand I can't do much about it. Okay. And most of you are happy about this. How much did you have to pay, by the way, for all the materials for this class? Yeah, 0. Okay, that's been my mission. It's been my main mission. Okay, outside of just teaching, that's been my main mission of my job. And so I'm giving a talk on this whole group that's doing all this calculus, it turns out, where there's no cost and it's new, cool material. So that's what my presentation is going to be on. But so again, most people like the fact that you don't have to pay. Okay, so it's for professors, though. I mean, you're welcome to come, but you'll be lost. Just let you know that. Okay, maybe bored, but the professors hopefully will like it. So just note that I'm not going to be much available that weekend. Okay, so you want to send me a rough draft. Make sure don't wait till the last minute on it. Okay, the requirement is Thursday at 8 in the morning, and I might be able to look at it on Thursday, but I'll be rushing. If you give it to me like Tuesday, then I'll have a lot more time, if that makes sense. Okay, so that's important. So in the project, same thing, you're going to use a spreadsheet. Just let you know, let's see if I got it up. No, let me put it up. It's the same spreadsheet. So if you've already, made your copy of it, it's the same sheet, nothing changed. The big changes, this is project 2. And in project 2, you're going to use 2 Verstats. So the first thing you're going to do once you open your spreadsheet is you're going to click on this tab 2. And next week, we'll talk about what all this stuff means, because we'll do 2 variable statistics. So just a note that you're going to be using 2 variable stats for the project. Got it? Okay. You're still going to be pretending you have a client, someone who might pay for your work done. So that's still going to happen. Okay. And again, it's in theory, but you should identify who it is. You're going to have to identify your population. One main thing that's very different between project 1 and project 2 is for project 1, a big, huge part of it was understanding good sampling technique. Project 2, I don't care at all. You're welcome if you want to use convenience sampling. Just admit to it. I don't take off points if you say we use convenience sampling. I did on project 1, but not on project 2. You also don't have to survey people. Okay, you have to collect data though. Okay, you're gonna have to collect data, and that's going to be important. So you don't have to ask people the anything. You can if you want to, but you can also just collect data. You can go to, some people have gone to like 2 supermarkets and compared prices at 2 supermarkets. And you walk into the supermarket and you write down the prices of, 31 items, and you walk into the other one and you write down the prices of the same 31 items and see which is more. Does that make sense? So you don't have to do a survey of people, unlike project 1 where you had to, because project 2 is not all about the sampling technique. Okay, project 2 is all about the confidence interval and the hypothesis test, which will be for a difference, which we're not ready to talk about yet, because that's next week. Any questions on that idea? Okay, so again, most important is by the end of, I would say in the next 7 days, next 6 days, actually, I'd say in the next 6 days, you have a partner. Got it? And recommend is a group of 3. Okay. And then after a week, in 6 days, then I'll talk about the details of the 2 sample type thing that you'll understand. And then that week, so in week 8, you should have your sampling technique. And just like you did in project 1, except now, instead of project 1, what you'll do in the discussions, you'll go to project 2 discussion forum, and you'll post your idea in your project 2 discussion forum. Okay? So I split them up. One thing is there's just too many people in project 1 discussion forum, so it's easier not to get lost in all the different comments. So there's a new project discussion forum. It's called project 2 discussion forum. And that's where, again, you can post for looking for partners. And also you should post in a week or so what your idea for your project is. And what you should post is in words and in symbols what your hypothesis is, what your null and alternative hypothesis is, who your client is, okay, possibly how you're going to collect your data. That's what you should post. And then I can look at it and let you know whether it'll work or not. Any questions on the idea? It's too early to talk about all the details because we haven't learned them yet. That's next week. So, and our next webinar will be Monday evening at 6 o'clock. And that's when I'll go over the last bit. So when you're ready to post, your project idea, which you won't be until after Monday, what you'll post is your null hypothesis and your alternative hypothesis. Kind of, we talked about that today, but it'll be with 2 samples instead of one. Okay. And that we'll talk about next week. So you'll post those in symbols and words. And then you'll also post who your client is and how you're going to collect your data. Does that make sense? Okay. So that's the idea, and I'll talk about it more next week. I want to do some now and more next week so that we have time next week. Next week is actually shorter in terms of new material because this week is, I don't know if you noticed, there was a lot to talk about for hypothesis testing. Okay, so we're kind of close to, my goal, usually between an hour and 20 minutes, an hour and 40 minutes, and we're an hour and 25 minutes, so it's about right. So I think I'm going to stop the recording. And then what I'm going to do is always open to questions if you have more questions after. And I drop my sharing also, but let me stop the recording.